So now let's look at chapter 10 etching process. So there are two types of etching, dry etching and wet etching. So the wet etch is cheap and simple, but hard to control. It's not so reproducible. It's not popular for the micro and nano fabrication. For the dry etch, so we use gas phase etchant in the plasma. There is both chemical and physical etching process. So physical is the same as the sputtering process as we have seen in the sputter deposition. So the dry etch works for many dielectrical materials and some metals. For example, so when we have aluminum, we can use chlorine gas to form aluminum chloride. So this one is volatile. So the etch will keep forward. For titanium, we can form titanium tetrachloride, chrome, O2Cl2. So they are all volatile. So those methods can be etched by the dry plasma etching process. For other methods, we have used ion milling. So ion milling is similar to the sputter deposition process, but it is more energetic. For example, if we want to etch a silver, so if we use chlorine gas, it forms a silver chloride. This one is a solid. So it's solid. It is not volatile. So the silver cannot be etched by the chlorine gas. So then it has to be etched by the ion milling process. So the etch has 3 steps. So the etchant transports to the surface. Then there is chemical reaction. Then etchant leave the surface. So now let's look at the figure of the merit. So first one is the selectivity. The selectivity is the etching rate ratio between different materials. Usually we want higher selectivity. That means we etch one material much higher. The etching rate of one material much higher than other materials. But generally, chemical etching has very high selectivity, so physical etching has low selectivity. So what determines the selectivity for the physical etching? Well, this is determined by the sputter yield. So the material that has higher sputter yield will be etched way faster than the material with a smaller sputter yield. So normally the sputter yield is 1 to 5. So the selectivity between the different materials is up to 1 to 5 selectivity. For the microfabrication or nanofabrication, the selectivity is usually between the film material and the mask material. For example, in this case, we want to etch this film material, use this material as the mask. This one can be the resist. This can be a photoresist. So, as you can see here, so when we etch into these steps, the Y steps, the mask etched by X. So the selectivity, selectivity is given by Y over X. In this case, this is not very good because the Y and over X, this number is not large enough. So here is you can see, so when the selectivity is low, so we have the mask lateral etching, and this is called the mask erosion. So this is not good. So normally we need a high selectivity between the mask material and the film to etch. In this example, we have the group 3 and the 5 semiconductor materials. We know group 3 is the boron, aluminum, gallium, indium. Group 5 we have those materials. We can see here, this one indium, aluminum, arsenide. So the indium and aluminum come from the group 3. So this will be indium X, aluminum 1 minus X, gallium arsenide. But this one is gallium arsenide antimony. So you see arsenide and antimony is group 5. So this one should be gallium arsenide X, antimony 1 minus X. So those are the group 3 and 5 semiconductor materials. This is indium phosphide. This one, so indium phosphide. So this indium gallium arsenide, indium gallium arsenide. So this will be X, 1 minus X. So we can do, in this case, the etching rate of different materials is very different. For example, the etching rate of this gallium arsenide antimony and the indium aluminum arsenide, so the etching rate of this layer is much lower than the etching rate of this indium phosphide. That's why. So we have this very large lateral undercut etching. The next figure of merit is anisotropy. This is obvious, as you can see here. This one is isotropic. So the etching rate along the horizontal direction is the same as the etching rate of the vertical direction. But this one is anisotropic, so faster etching along the vertical direction than the lateral direction. But this one is completely anisotropic. We have only vertical etching. But normally this is what we want. We want vertical etching. This way we can maintain the opening, the size of the opening. So this isotropic is similar to conformal. So for the thin film deposition, we talk about conformal deposition. So this conformal deposition is similar to the isotropic, lateral etching, vertical etching, the same way. But generally speaking, so chemical process like wet etch or platinum etch give you isotropic etching, and the physical process, we have the bombardment, we have argon, iron, or we have maybe other ions like chlorine ion. So we have this bombardment. But this physical etching, this physical bombardment process give you anisotropic etching. The isotropic etching is good, it's okay, not bad, it's okay. With large features and the sidewall slope does not matter. Or with large critical dimensions, for example, large feature size. There will be large feature size loss, but this is not good for the nano fabrication. But it's quick, easy, and cheap. So for the anisotropic etching like this one is good for the small features and with vertical side walls, and it's good for the nano fabrication with the very good profile control. But this one normally costly, so we need a platinum etching machine. And now first look at isotropic etching. So the isotropic etching is the wet etching. So wet etching was used in the 1970s for the IC. For the IC, wet etching was used till the 1970s. And then when the feature size becomes smaller and smaller, so the industry shifted to the dry etching. For today's IC manufacturing, so wet etching is used only for the non-critical feature sizes. So advantage, very high selectivity, cheap machine, inexpensive equipment, batch system with high throughput and etch rates can be very fast. The disadvantage, the main one is the isotropic etching profile. Isotropic. This one is the problem. As you can see here, we have the mask. So after the etching, because this is isotropic, we have this isotropic etching. After removing the mask, we have this one. If the opening here like 10 nanometer, for example, 10 nanometer, then the opening here become maybe 50 nanometer. So you can see, so this is very bad. So we lose the feature size. And also high chemical usage and poor process control, not as well controlled as the dry platinum etching, and there is particulate contamination. So the etching rate for the wet etching is controlled by the three process. So the reactant comes to the surface, and chemical reaction on the surface, and the reactant, and the reaction product transport away from the surface. So normally we want reaction rate controlled process, because if the etching is controlled by the reaction rate, so we can control the temperature. So when we have uniform temperature, we get uniform etching rate. Because temperature of the liquid is easy to control. On the other hand, when we have the mass transport control the etching, for example, if this is the wafer here, if we have the mass transport, you can imagine the mass transport to the edge will be faster. So then the edge will etch faster. So normally we do the stir to minimize this effect. So the first example is the etching of the silicon oxide. But this one we use hydrofluoric acid. So normally it is diluted. For example, 6-water 1 HF here is 49%, but the HF here is 49% HF. So this is what you get when you buy it. This gives you 120 nanometer per minute, undiluted 1 micrometer per minute. So we have very high selectivity between silicon oxide and silicon. So that means the etching will be stopped at the silicon. To give you more uniform etching, we sometimes use, it's called buffered HF, BHF. It is also called buffered oxide agent. It's also called BOE. So in this case, we mix ammonium fluoride with hydrofluoric acid with HF, normally 6:1 ratio. So how will this help? You can imagine we have this reaction. So when the HF goes down because of it is consumed. When the HF when the HF is consumed during the etching process, so we have chemical reaction to the red side, but this one will release more HF in the solution. This way, we can maintain the etching rate at different places. So how to tell, so for the HF etching, so how to tell all the oxide is gone? So how to tell the etching is done and all the oxide is gone? So this can be tell like this. At the beginning, so this is the hydrophilic. So we have hydroxyl group, so this is hydrophilic. So after all the oxide is gone, it becomes like this. So this one is hydrophobic. So you can see if you take out from the container, if the water fall off, you know it is hydrophobic. Then you know all the oxide is gone. So the etching rate increase with the temperature, but this is normal. So whenever you go to the clean room, usually there is special training for the HF. So this chemical is very different from other chemicals. So we need special training, otherwise you are not allowed to use it. So this is because it's not so strong. So normally we use diluted, like 6:1 diluted. So when they are very much diluted, you don't feel it. You do not feel the pain for the diluted HF. And it looks like a water. You cannot see it. And it penetrates the skin and attack the bone. And when you feel it, the bone is already attacked. But this is more dangerous people think this one is dangerous. Sulfuric acid is dangerous. But this one is only burn the skin. Only burn skin. And you can feel it. You feel it, they will run away. So you can minimize the burning of the skin. But for the HF, it can corrode the bone, it's more dangerous. The second example is the isotropic etching of the silicon. So the idea is very simple. So first we convert silicon into a silicon oxide. Then we etch away the silicon oxide. By the hydrofluoric acid. So to convert silicon to silicon dioxide, so we use the nitric acid. When we have the nitric acid is partially decomposed into NO2. This one will oxidize the silicon to form the silicon dioxide. Then the silicon dioxide will be dissolved by the HF. Then the etching will keep going. So sometimes we can use the water as the diluent. We can also use the acetic acid as the diluent. So here is the etching rate. So first, this is the each of the lines they have the same etching rate. For example, this one is 482 micrometer per minute. So this is extremely fast. But normally we have etching like a few hundred nanometer per minute. This one is a few hundred micrometer per minute. So that means along this line, the etching rate is 482 micrometer per minute. So this is the percentage of the nitric acid. This is the percentage for the acetic acid. But this one is the percentage for the hydrofluoric acid. So how to read this curve? For example, how to read this graph? For instance, if we have here, if we talk about this spot here, you draw a line parallel to this axis, you get 40%. So we have 40% nitric acid. You draw a line parallel to this one, 30% acetic acid. And if you draw a line parallel to this line, you get 30% hydrofluoric acid. In total, you can see it is 100%. So how come they happen to be 100%? This can be proof. You can see this one. So percentage for this one is given by Ag. And this one here, 30% here is given by Ce. And this one here is given by this one. You can see so this one is the same as this one, right? This one is the same as this one, and this one is the same as this one. So overall, you can see Ag plus Ce plus Bd, Ag is equal to 100%. That is how you read this graph. So there are region 1 and region 2. So high HF concentrations, so the reaction limited by the nitric acid. The reaction rate is limited by the nitric acid concentration. This will follow constant nitric acid percentage line. You can see here, constant nitric acid 10%, like this. For region 2, we have high nitric acid concentration. Then the reaction will be limited by the hydrofluoric acid. This one follows is horizontal. They are like horizontal, follows constant HF lines. So in this region, here, it is polished. In this region here, it is rough. So how come this region here is rough? So now we need to come back. So for this etching here, so the etching we have, so etching we generate this one, we generate HNO2. This is the catalyst. So for this etching to proceed, we need a catalyst. And this catalyst is HNO2. For example, if this is the silicon surface, it happened that there is HNO2 at this spot. Then this area will be etched. So this is the catalyst. So this area will be etched. And during the etching process, we generate even more HNO2. Then this area will be even more etched. You can see this is a positive feedback. So when we have positive feedback, it's not stable. So that means this area will etch a lot, this area will etch very little. But in the end, we get rough. We get rough surface. So when we have high HF, so the HF will be enough to remove all the oxide. Then we get a rough surface, as we said here. So this area will be rough because we have the high HF region. So the reaction limited by the nitric acid. So this one we have this positive feedback to have the if the etch starts here, it will generate the catalyst, then it will etch even more. So the second question is, can we replace nitric acid with hydrogen peroxide? So we know hydrogen peroxide is also oxidizing agent like a nitric acid. So the answer is, if we use this one, it will not etch silicon, but we can add. We need is a catalyst. We need a catalyst. So in this case, we can use the metal. We can use metal as the catalyst to help the etching of this chemical to etch the silicon. So this is called metal associated chemical etching. So MAC etch is called MAC etch, metal associated chemical etching. So we use hydrogen peroxide plus HF plus a catalyst, which is a metal, a noble metal. So this is actually a very popular research area. So I will show you some papers. So I just searched metal associated chemical etching. You can see this review paper is cited 1,700 times. So that means it's really popular. This very high citation. So this is the paper. This is the review paper. So here we have the noble metal as the catalyst. Look at this graph. So the noble metal includes gold, silver, platinum, and palladium. So all those metals can be used as a catalyst. But gold is the best because gold is chemically stable. So gold will not be etched away. If we use silver, the silver will shrink because silver will be etched away by the HF. So we have HF. This one will attack silver, but HF will not attack gold. So normally we use gold as the catalyst. So in this area, in the contact area, so when there is contact, so this region here, when there is contact, there is chemical reaction. So that means the silicon below the gold will be etched away. So there is no etching here, but the silicon below the gold will be etched away. As a result, the gold will sink into the silicon. So the area in contact will be etched away then they are dissolved, then the gold will sink into the silicon. As you can see here, so those are the. Look at this one. Just see, but this one here, it should be gold. Yeah, so this is gold particle. But this one is the gold particle. You see the gold particle sink into the silicon for the etching process. Because this one also gold. It's really deep, really very, very deep. But this one, because this one, see, you see the gold at the bottom. So this is the silicon. Those are the silicon pillars, very, very high aspect ratio silicon pillars, and the gold sink onto the bottom. So this is a very, very nice etching process. Now here we have the height, maybe 12 micrometer. So I see people, they can etch like a 400 micrometer. So they use this method to etch 400 micrometer, very, very high aspect ratio aspect. So very, very high aspect ratio silicon structure with 400 micrometer height. So this is very, as I said, this is really a very, very nice and popular etching method. So now we look at the etching of the silicon nitride. The silicon nitride can be etched away by the HF. So here we call it BOE. So this is the BOE. The BOE is the buffered oxide etch. So we have the ammonium fluoride and HF mixture. So this is BOE. For example, the etching rate is 30 nanometer per minute of oxide, and the silicon nitride is 5 to 15 angstrom per minute. The etching rate is slow, but it etches. For the undiluted HF, undiluted at about 50 nanometer per minute. This is okay, 50 nanometer per minute. More popularly, a silicon nitride is etched by the phosphoric acid. You can see here. So here is the silicon nitride etching rate, but we need a very, very high temperature. For instance, if we 10 nanometer here, the drawing not very good. So to get 10 nanometer, so this is already a slow etching rate. So we need nearly 180 degrees. So we need very high temperature for the etch. But you may wonder, how come we can have 180 degrees? Because this one is in water. So this one, phosphoric acid is in the water. 180 degrees, the water will be all vaporized. Actually, as you can see here, at this temperature, we get 91.5%. So at the lower temperature, we get 80% phosphoric acid and 20% water. At this very, very high temperature, we have 91.5% of phosphoric acid, and we have only 8.5% of the water. So this solution is very sticky. It's very, very sticky. So this is how you etch away the silicon nitride. For the metal, here we talk about aluminum. So aluminum can be etched away by the mixture of phosphoric acid, water, and nitric acid. And this one is the acetic acid. So first we use nitric acid. We use nitric acid to convert aluminum into aluminum oxide. Then aluminum oxide will be etched away by the phosphoric acid. This will generate the bubbles. The bubble is caused by the hydrogen. So the aluminum can also be etched in the acid and diluted acid and base. For example, all those acids and the base will etch away the aluminum, but they are not very controllable. For example, the etching of the native oxide very slowly, and suddenly the etching aluminum will be very fast. So the etching rate is not controllable. On the other hand, when you use this one, because anyway you convert aluminum out to aluminum oxide. You convert aluminum into aluminum oxide. So then etching is always aluminum oxide. Then etching will be more controllable. The better is if you use diluted 100 diluted HF, this is also etch away the aluminum, and this is normally what we use. And we can also use here I didn't say TMH. This is the tetramethyl ammonium hydroxide. But this is the developer for the photolithography. So this table summarizes the etching of different materials. What etching of different materials? We have talked about silicon. We have talked about silicon oxide, silicon nitride, aluminum, silicon. So this also silicon. Titanium can be etched away by this mixture. It can also be etched away by the HF. HF can also etch away the titanium. It can be very diluted HF. This titanium nitride photoresist we can use the Perina. For other materials like gold, gold can be etched away by the iodine, by this solution iodine. Gold can also be etched away by the mixture of 3 hydrochloric acid and 1 nitric acid. This is called aqua regia. For all the metals, many metals they can be etched away by the acid, but titanium and chrome cannot be etched by the acid. So titanium can be etched by the HF or by this solution here. Chrome can be etched by the ferric ammonium nitrate plus acid. So now we look at anisotropic etching of the silicon. So here we talk about anisotropic etching of silicon. Other materials like gallium arsenide, like those 3, 5. So other materials like gallium arsenide, there's also a group 3 and 5 semiconductor, can also be etched anisotropically by the QH. But here we only talk about the etching of silicon. So this is roughly this is the mechanism. So the etching rate of the 111 is much smaller. The etching rate of the 111 is much slower than the etching rate of 110 and 100 and other planes. So this is because the 111 has the density of the planes has the closer packing of the orientation. So 111 has closer packing, so the etching rate is much slower than the etching rate of the other orientations. For example, it can be a few hundred times slower. This is very high selectivity. So another better explanation for the etching rate difference is because of the bond, dangling bond. For the 111 plane, so it's something like this. So this is the silicon, but this is the surface. So this is silicon. Above the surface is the hydroxyl group. Look, you can see we have only one 111 has only one dangling bond. The one above, 3 below, three bonds below. So this is stable. If we talk about 100, this is 10. This is 100 plane. If we draw a plane here, so you can see silicon like this. OH, silicon. This is the surface. So we have two dangling bonds. For the 110, if you draw it here, you draw 110, it's also like a 2 bond. But this is why 111 plane etch rate is much lower than the other planes. For example, we take this is a combination 250 gram KOH, 200 gram of IPA. This isopropanol is also called 2-propanol. This one can be replaced by the water, so we do not have to add IPA. If we have QH in water, this will also work. For example, this one is 30% QH in water, no IPA. So IPA is kind of a surfactant. So this will, when you have the surfactant, it will help hydrogen to go away, reduce the bubble. But this one give you smoother etching than without it, because this is a surfactant to help to remove the hydrogen bubble. So the etching rate, so 111 can be 1 to 600 to 400. So 110 etch much faster than 111, and 100 also much faster than 111, and this one etch the fastest. But this is very high selectivity. So the etching rate go up with the temperature. So typically we do the etching at those temperatures. We get about, if you look at here, this 60. We get about 60 micrometers per hour. That is 1 micrometer per minute. So for the silicon, when we use QH, it's about 1 micrometer per minute at this condition. For the EVP, so we will talk about EVP later on, it's a similar rate. So the etching rate of silicon oxide is 40 to 80 nanometer per minute. So the selectivity is pretty good. For the silicon nitride, the etching rate is much lower, even much lower. So you can see the silicon nitride is the best mask material for etching the silicon using the QH. So because the 111, so the 111 etching is so slow, as a result, the moment we have the mask, so this is the mask. We look at here, this is the mask. So this mask here, this mask can be silicon oxide or silicon nitride or chrome gold. The best material is silicon nitride. So then the etching will be stopped at the 111 direction because the 111 direction etch so slowly. The etching rate of 111 is very, very slow, so it's stopped. So then we have this angle here, 54.74 degree. So here the same thing. So here the ICM image you can see stops at here. When it reaches to the bottom, the etching will not proceed. So how to get this angle? So this is the angle between 111 and 001 plane. So this is the 111 plane and this is the 001 plane. So how to calculate the angle between those two planes? So then we have to look at what we have learned previously. So this is from chapter 3. Wafer fabrication. For any plane LMN, it is always perpendicular to the direction LMN. That means the angle between two planes will be the same as the angle between two directions with the same index. So now I come back. So the angle between 111 plane and the 001 plane is the same as the angle between 111 vector and 001 vector, because this one is perpendicular to this plane and this one is perpendicular to this plane. So the angle between them is the same as the angle between those two vectors. So how to calculate the angle between the vectors? Vector A equal to 111, vector B equal to 001. So we know that A, in this case, is 1 times 0 plus 1 times 0 plus 1 times 1 equal to 1, which is equal to A cosine theta. Theta is the angle between the two vectors. So you can see A equal to square root 3, B equal to 1 cosine theta. So cosine theta equal to 1 divided by square root 3. So that theta equal to 54 times 7.4 degree. So those are the examples for the etching process. So here, in this case, for this one, so we have, this is the 111 plane. This is the 111 plane. We can make a structure like this. This can be used for the bubble jet printer nozzle, inkjet printer nozzle, because we can make something like this. But this is why we have the concave corners. So when we have the concave corners, it's limited by the slowest. So when we have concave corner, so the plane is confined by the slowest etching plane, which is always 111. But for the convex corner, then the boundary will be the etching plane will be the fastest. Plane. So for the convex, it is the fastest plane. For the concave, it is the slowest plane. For example, if we look at here, this one we have the window, we have a square window here. So this is the mask. At the beginning, this one will etch down. It will like 111, 111, 111, and 111, like this. At the beginning, they all etch down like this. But after some time, so this is the convex. So this is also convex. For the convex corners, it etched like this. right? It undercut like this. Then eventually undercut like this. Eventually we get something like this. So that means the corner here is convex. Eventually we get something like this, because if you look at this circle here, this circle is mostly convex. Then the fastest plane will determine the shape. This plane here can be, for example, 331 plane. So the slowest plane is always 111. The fastest etching rate plane can be 311 or can also be other planes depending on the etchant. So now we can I can show you a paper. So if we look at this paper here, so this is the paper one. This is the paper. So you can see. So this 311. Oh, here. So this 311 is the local fastest etching rate. As a result, in this case, the plane here, the sidewall here will be a 311. Now this is for the case of the convex. If the mask, so here we have the mask like this. We have the mask. Here the mask like this. If we have the opposite, if the mask. So here, if we have the mask outside of the square, outside of the square, then we got something like this, right? We got something like this. This is the concave. So we have the 111 plane. All of them is 111 plane. So we can use this process. to make the AFM props. So here we pattern the mask. Then we do the etch. Then in that we get this plane. So here you can see this one may be 311 plane. Or it can be other planes depending on the agent. So the fastest etching depends on the agent. The slowest etching is always 111. So this is the 100 wafer. So when we use 110 wafer, if the greeting line is well aligned, we can etch vertically. We can etch very, very vertically. We can actually get something like this. You can keep etching, you can get very, very nice, very isotropic etching. I can show you a paper again. So this paper is from our group and it's published last year. You can see how nice it is. So we can really etch very, very deep and narrow, very high aspect ratio trenches by using the 110 wafer. So now the question is, so what is the direction? What is the direction along the greeting lines? That means what is the direction along the lines? So now we know that. So the side, this is a 111 plane. Okay, so if we take the vector, it will be 111 vector, and the top is 110. So you can see, so we have A equal to 111, B equal to 110. It should be 1 minus 10, because so that this one and this one, they are perpendicular to each other. You can see here A equal to 1 times 1 times minus 1, so equal to 0. That means this one, they are perpendicular to each other. So now we want to know this direction. So this direction here is perpendicular to 111. It is also perpendicular to 110. It is perpendicular to both of them. Then we know that this direction, if we talk about C equal to A cross B, right? We know. So the C is perpendicular to A and C is perpendicular to B. The direction of the C will be A cross B. It is perpendicular to both of it. Then we have this one. So it's 1, 1, 1, 1 minus 1, 0. So I hope you can remember the matrix calculation. And then you have this. You have I minus J minus 2K. So this is given by 1 minus 1 and minus 2. So now we can look at this equal to C. So C is along the greeting direction. But now we want to see so whether this C is perpendicular to A or not. You can see the 1 yeah, so sorry, this will be a plus. This one here should be plus. So this is plus. 1, 1 minus 2. So I write it here. 1, 1 minus 2. You can see C and A. So 1 times 1 plus 1 times 1 minus 2 times 2. So you can see C dot A equal to 0. So they are perpendicular. C and A perpendicular to each other. The C dot B. So C, you can see so 1 times 1 plus 1 times minus 1, so it can equal to 0. So they are also perpendicular to each other. So that's why we know that. Now we know. So 1, 1 minus 2 is the direction along the grating. So besides QH, we can also use TMH and EDP. So TMH is the tetramethyl ammonium hydroxide. So this one is used for the positive resist developer. So we have seen this. We have seen the TMH in chapter 5 when we talk about optical lithography. So the temperature is the same to the QH. The etching rate is also close, but the selectivity, the etching rate selectivity between the 100 and the 111 is not very high. This is 10 to 35 times. For the QH, we know we can get 1 to 100 times selectivity between 111 and 100. The surface is rougher than QH. It will attack aluminum, and we can use boron stop etching. So we will see this one later on. And we have good selectivity to oxide and nitride. It's better selectivity than the QH. It's better than QH for the case of the oxide. But this one is popular, so this is good. Another one is called ethylene diamine pyrochaticode. It's called EDP. So the etching temperature is higher, the rate is similar, a good selectivity does not attack those metals, but it will still attack aluminum. So selectivity between the 100 and the 111 is not very high, and we also have the stop, the etching stop. But this one is not popular. So because ethylene diamine is toxic. It's toxic, and also when we have the water in the air, because of the humidity. This one water will react with the ethylene diamine. If you breathe it, it's hurt. So this is as a result, but it's toxic and dangerous, and now that people do not use it very much. So now let's look at the etch stop, the boron stop etching. The idea is that so when the silicon is heavily doped with the 10 to the power 19 to 10 to the power 20 boron, the etching rate drop a lot. That means when we have heavily doped p-type silicon, then etch, then at the doping layer, heavily doped layer, the etching will be stopped. So this is called etch stop. So this one, it is useful sometimes, but it is not that useful. So the problem is, so boron is different from silicon. So we have a 10 to the power silicon, 10 to the power 20 boron into 10 to, we know for the silicon we have 10 to the power 22 silicon. So it's already like 1%. When we have 1% boron into the silicon, the material has a high stress because the size of the boron atom is different from the size of the silicon atom. So we have this stress. So the stress is a big problem for the MEMS, micro electromechanical system. As a result, so this one it is useful, but it's not that useful because of the stress. Okay, thank you.